All right, so for our next kind of chunk of stuff that we're talking about, we just finished up talking about waves, which was a good introduction actually into this next unit. So we're actually going to cover optics, and we're going to break this into kind of three distinct chunks. The first chunk we're talking about today, and that is going to be treating light. So optics is like the study of light, and part one is treating light like a wave. Now, there's the wave model of light. Next week, we'll talk about the ray or particle model of light. And then we'll just get a little bit of an introduction into wave particle duality, because light is a very complex thing. So, we're just kind of giving an overview of each of the three views of it. We're not going to get super detailed, and we're not going to get into the math really behind it, but rather we're just going to talk about a couple of the physical proofs or physical evidences that treat light in these different manners. So what is light? Under some circumstances, light acts like particle traveling in straight lines, and we see this all the time when we look at like lasers. Lasers travel in a straight line. But in other circumstances, and this is what we're focusing on this week, light shows the same kind of wave-like behavior as sound or water waves. The waves that we just studied, right, where it's propagating out, and we talked about intensity and we talked about stuff like that. Like light also exhibits those types of behaviors as well. But if we change the circumstances yet again, we actually see that light exhibits behavior that is neither wave-like nor particle-like, but rather has characteristics of both. So we developed three different models of light. Each of them takes a look at specific circumstances and explains why light is acting the way it acts in those different, I call them domains or different circumstances. So that's what optics is really, it's a couple different branches that helps describe what's going on with light. And throughout the course of history, as we've understood those different branches better and better, we've gotten a better and better model of what light is. So the first model is the wave model. And this is, I always think it's funny when I say it this way, this is widely known for the fact that light acts as a wave. It's certainly true that under many circumstances, light exhibits the same behavior as sound and water waves, and we're going to take a look at that in this first section. Lasers and other devices use the wave model of light to work, such as like DVDs and CDs and Blu-rays. Those all use the wave model of light to work, and the study of light is called, as a wave, is called wave optics. We will also take a look at the fact that light travels in a straight line, and this will get us into the ray model of light, and we'll look at light rays. The properties of prisms, mirrors, lenses, and other optical instruments like telescopes and microscopes help us describe light acting as a ray. Unfortunately, it's hard for us to know that light travels in a straight line with the statement that light is a wave. So those two things kind of contradict each other. So we'll look at a principle that kind of ties them together. So for the most part, waves and rays are exclusive in their own areas. So they're the things that we're going to study, it's when you look at it a certain way. So an important task will be to see when each model is appropriate. The ray model of light helps us with ray optics, and that'll be the next lecture next week. Finally, there is the photon model. And this has been, because hundreds of years ago, there was a lot of, not hundreds, a couple hundred years ago, there's a lot of debate on what the correct model is. And with modern technology, specifically, Einstein did some experiments and got us into the realm of quantum physics. Light consists of not rays or waves, but rather photons that have both wave-like and particle-like properties. So photons are like the quanta of light. They're the energy of light. And much of the quantum theory is beyond the scope and sequence of our class. Don't worry, we're not going to be getting into a ton of quantum physics, but we'll take a peek at a couple of the important ideas in the third mini lecture that's going to be during our week of testing. Now, this is actually a common misconception. Einstein won his Nobel Prize in Science based on the photoelectric effect, which treats light like a wave-particle duality. So let's talk just a little bit today about the wave model of light. So if we have, we can actually step back and look at some water. And often in class, I'll do something called a ripple tank. And a ripple tank puts waves of water. There's a little like dabber right here that just dabs in it, and it sends out these waves. Now, once these waves hit this opening right here, only some of that wave is allowed to go through. So here we have these wave fronts. But once it leaves these openings, it kind of acts like a speaker, right? We see these curved lines that act, I just screwed that up, that act just like a speaker. And therefore, we actually get this concept known as diffraction. And diffraction is when the wave spreads out beyond the opening to fill the space on the opposite side of this barrier right here. So diffraction is a clear sign that that a wave is passing through an opening, and we get that from what we learned about previously when we talked about waves last unit. Now, if the opening is too large, so here we have just a super large opening, we can see that it's barely spreading. Right there, it's not spreading out at all, but just beyond it, it is barely spreading out. There's this little bit of energy that's being pushed out outside of the barrier. And this actually is a great explanation for what's happening when we have shadows. So the wave, and we see it in this picture below, there's these large openings that light is allowed to travel through. And on the opposite side of that, so it cuts out where the light can actually go through. And then there are some shadows just outside of that. So there's no significant amount of light that hits that area, and that's why it appears dark, or that's what a shadow is. This is similar to the straight lines, or evidence that the straight lines can come through and they go through that opening without spreading out. So whether or not a wave spreads out or travels straight, it's still going to interact with the objects around it, and how it interacts depends on the objects around it. So diffraction, this concept of diffraction we talked about in the last slide, only becomes noticeable when the opening is comparable in size to the wavelength of the wave. And what does that mean? It means that I got these barriers here, right? And this opening right here, it's not even close to being comparable to the wavelength of the wave. Now, when we talk about light, when we talk about visible light, we're talking between 400 and 700, not meters, but nanometers. So times 10 to the negative 9th meters. Very, very, very small wavelength. So if our barriers are too far apart and we have too big of an opening, we're not going to see the wave nature of light. So we do know a couple things already. Or we would study it, right, in different ways. Light is an electromagnetic wave, and I've talked about this concept before. We talked about it last unit, and that is that it has an electric field and magnetic field, and they propagate with each other, and that's what allows it to travel through a vacuum, unlike sound. Light travels at the speed of light. It travels at 3.0 times 10 to the 8th meters per second. The visible light, I just mentioned it, has a wavelength between 400 and 700 nanometers. That's in the visible spectrum. Now, when light hits or changes mediums, such as water, glass, or air, the light waves, the speed of them will actually slightly slow down. And then, since the waves are slowing down, it'll actually give us this perception, and you can see this in this picture right here, of bending. And this is known, or the concept that helps us understand this is known as the index of refraction. So we'll talk about, in this unit, we'll talk about reflection and we'll talk about refraction. And refraction just means that that light is going to bend a little bit because of its changing in medium. So on the outside of the cup here, it's air. And then inside the cup, we have water. And technically here, we have glass. So because the light it's coming from your eye, or it's coming from around you, and it hits off this pencil, and it reflects back. Because of refraction, it looks like it's bent. Now, we're not going to really get into anything huge mathematically here, but when light travels, the frequency of light, remember from last unit, frequency, does not change as the wave moves from one medium to the other. This is important because frequency characterizes the color of light, right? So if it's green light and it hits water, it's still going to look green. So what's actually happening is that the wavelength of light is changing based on what that index of refraction is, what that material is. So the wavelength is shorter as it goes through a higher index and it changes mediums. So that's why light tends to bend. And this is important evidence of the wave nature of light. So a big thing that we'll look at is, because light acts like a wave, just like we had towards the end of last unit, we had sound waves interfering with each other. We can also have light then should be able to interfere constructively and destructively. So we have a couple different big studies in physics that help us explain the wave nature of light based on this concept of constructive and destructive interference, just like we talked about last unit with sound waves. So if they have the same properties of waves, and I think I mentioned this at the beginning of last unit, when we're talking about studying waves, we're talking about any kind of wave. It doesn't matter if it's sound or water or light. They should all have the same behavior. And that's what we're actually going to see with a couple different experiments. The first experiment is Young's double slit experiment. So here I have a laser beam coming through, right? And it's hitting this piece of paper, and on this piece of paper there's these two narrow splits, and they're some distance apart. Now, if light just acted like a ray, right? So it would go through these two slits, and then on the viewing screen we would simply see two straight lines, right? Sorry for the blue, I'm just trying to make a point here. So we would simply see two straight lines. However, when Thomas Young did this experiment, and this is what helped him prove that light acted like a wave, we see not two straight lines, but we see an interesting pattern on the viewing screen. And the reason is the same concepts that we talked about last unit. We have these waves coming out, and anytime that we have these waves meeting with each other perfectly, and that's where I'm drawing all these very nice dots, we get constructive interference. And then that constructive interference makes a bright image, or what we call a bright fringe, on the viewing screen. So that is super good evidence that light acts like a wave. So his double slit experiment, again, we're not going to get into the math behind this, but the light will spread out beyond each slit, and it's going to get some constructive interference at certain distances. Don't worry about this. And with constructive interference, we're going to get a high intensity of light, and then we'll also get destructive interference. And then with destructive interference, we're going to get a low intensity of light. So right in the middle of this slit right here, we have what we call the central maximum. That's the brightest fringe, and that's because that's where all these waves pile up. Now, as we get further and further away, you see this nice, neat pattern of successive fringes. And as they get further away from the central maximum, they get dimmer and dimmer and dimmer, but they're all characterized by these specific bands of brightness. Now, in between these bands, so right up here, not a great picture, but there we get what we call dark fringes. And the dark fringes is when we get this destructive interference. So the light waves, there's a crest of one wave and a trough of the other wave, and those waves cancel out, and that's where we get darkness. So again, more evidence that light does act like a wave. So when we look at, if we were to graph the intensity, so intensity is how bright the light is. Sound intensity is how loud sound is. So we get these, if we were to graph the intensity, right at our central maximum, we have our highest intensity. And as we go further and further away from that central maximum, we get these bright fringes that all have just kind of falling intensities, right? So it gets dimmer and dimmer and dimmer, but directly in between that, we have immediate areas of zero intensity. We have immediate areas of darkness that is caused by destructive interference. So we have the central maximum that's bright, and then as we get further and further away from that, it gets dimmer and dimmer, but we always have these areas of absolute darkness. So you can actually do this yourself. It's really not hard to do it. You can get a piece of aluminum foil and cut two parallel slits very, very, very close to each other. We're talking about a millimeter apart from each other, using a razor blade or a sharp pen or something sharp that can give you a nice small slit. Now you hold the slits up to your eye and look at like a bright light. So if you look out the window at the sun, or if you're doing it at night, you can look at a street light. You'll actually see these patterns. So that's what this is these are just some double slits, and they're looking at light. And what do we see here? Well, we see these bright fringes, and then we see areas of darkness. I probably can't even point them out because they're so close together. So there's bright areas and dark areas, and that is caused by constructive and destructive interference. Now, the next step that was taken in the explanation of this is like, okay, well now instead of two slits, let's do a whole bunch of slits, right? We got all these slits and we're still shining light through all of these slits. This is known as a diffraction grating. And a diffraction grating is multiple slits in one device. We define it as the number of slits every so much distance. So it could be 1,000 slits per meter or 1,000 slits per millimeter or whatever. So it's a number of slits in a given distance. And those waves are going to come out, and they're going to come out as waves, and they interfere with each other and they make unique patterns. So here, for example, is grating with 5 slits, right? And what do we see? We see kind of the same concept as a double slit, but things aren't uniform as they go out, right? So I have this central maximum, like I did before. I'll always have a central maximum. And then I do have a slit that's just outside, or a band of light that's just outside. But look how far away the second band is. So it's not uniform like a double slit experiment. It gives me a slightly different pattern. And we don't really need to get into what that pattern is too much, but this is more evidence that light acts like a wave. So the more slits I have, the more, or the greater that the intensity of light is on that viewing screen, and the thinner that band is. So here's 2 slits per any given distance. We have nice thick bands here. Here's 10. Look how much thinner the bands are. Here's 50. Look, they're like laser thin. But it's all still evidence that light is acting like a wave. As we increase the number of slits, the bright fringes get narrower, and they get brighter because that intensity stays the same, but how that intensity is divided, it's divided in a smaller area. Utilizing this is this concept of spectroscopy, and this is a huge chemistry concept, and that's the science of measuring the wavelengths of atomic and molecular emissions. This is actually how astronomers and chemists can use emissions from things and determine what they are. And what do I mean by things? I mean things as complex as looking at a distant planet and the light reflecting at it from a nearby star and determining the chemical makeup of the atmosphere of that planet. It's gotten very, very, very complex. Not covered at all in this class, but is a really cool application of this wave-like nature of light. Then finally, let's simplify it. Let's get rid of 2 slits. Let's get rid of multiple slits. Let's look at simply 1 slit. And this single slit diffraction is, in my opinion, the greatest evidence that light has to act like a wave. It's a diffraction similar to the double slit, except guess what? There is only 1 slit. Now, what do we see on the screen? If light only acted like a ray, again, we would just get this one thin band that looks exactly identical to this slit. But instead, this is a picture of what we get. We have this thick, wide central maximum. Then we get these secondary bands that spread away, right? And we still get this area of blackness, this area of destructive interference. So we get very strong evidence that light is acting like a wave because of this single slit diffraction. And in order to explain this single slit diffraction, we have Huygens principle. And this is the only way that we can actually explain this because it doesn't make sense, right? If light's just going straight forward and I got this wave, it doesn't make sense that I have these unique diffraction patterns. So Huygens principle explains what's going on and it just gets you a geometrical model to visualize how a wave passing through a narrow slit evolves and makes these unique diffraction patterns. So it's got two main parts. First part, very important. Each point on a wave is a source of a wave. That means that for every little piece of that wave, it's creating another wave. It's creating a wave beyond that. So even if I have a straight line, if I were to isolate this one point right here, as this one point goes out, it's going to make a wave. So every single point acts like a wave. Then at a later time, the shape of the wave front is a curved tangent to all wavelets. What the heck does that mean? I'll explain that in just a second. So this is what we mean. A plane wave, a wave that's coming forward as a wave front, every single point on that wave is making a wave. But those points all add up to make one wave front that's tangent to all the wavelets. And even if we have a spherical wave, right, all these points are going out and it's making another spherical wave. So all these individual wave fronts add together to make a total wave front. And that's the second principle. It's a little confusing, but that's how he justifies the wave-like behavior of things like single slit diffraction. So if we're looking at single slit diffraction, again, we have some slit, and it's got some opening. We'll call that A. Again, we don't need to worry about the math behind this. I just want to be able to explain a little bit about what's happening. So according to the Huygens principle, each point can be thought as a source of that wave. So as it goes out here, every single point is acting as a wave. And it's not just looking like this. This would be like, oh, it's one point. And then we would get this like uniform picture on the screen. But instead, every point is going. And then we get all these areas, and my drawing is phenomenal. But we get all these areas of constructive and destructive interference. So what is the picture that we get? We get a nice, big, wide central maximum. And then we get these light fringes that get darker and darker the further away we get, based on constructive interference. And then we get these dark fringes, and that is where we get absolute destructive interference. So what do you need to do? That was an interesting little introduction into what's happening with the wave model of light. But you should have already completed Lab 9.1, and hopefully that gave you a little bit of an introduction to what we're talking about today. Just try to make it so that you can look at some of these shapes and what happens on the screen and question, why do things look that way? You should have filled out the graphic organizer as we went through this, or you can go ahead and pull open the notes. And then there's a quick homework assignment just getting you to look at a couple of these concepts. I think it's like 3 questions, a nice, easy introduction to the evidence, the proof, the fact that light acts like a wave.